final subject that we're going to be going over is the binary tree, right? So we're going to talk about what it is, how it works, how to use it, and how to code it. So basically, what a binary tree is it's a recursive data structure where each node can point to two other nodes maximum, right? And so essentially, it's very much like a linked list, right? But now it has a reference to a left and a right node, right? And so we can still use this to search, store, and organize larger sets of data because it actually reduces the time to do the work, right? If we're only working with half of the data set, right? Especially depending on how you organize it. A good example of this is actually, if we're searching through a dictionary, you're not going to go through each word one by one to find the definition of that word. You might do something along the lines of go straight to the middle, determine if you need to go, maybe a little bit higher, a little bit lower, depending on what word you're looking for. Same thing also with a family tree. That's a perfect visual example of a binary tree, right? So essentially when we're adding and searching and when we're adding in elements into the tree nodes, there's several different ways that we can add things in to kind of organize it. One very popular way is a lexicographical order. What this means is that we insert something to the left and then we insert something at the root, which is the main node, and then we insert something at the right side, right? And so this is what allows us to be able to store information in a very organized way. Essentially, with lexicographical order, when we insert something to the left, it means that it's smaller or it's least, or when we're inserting something to the right, it means that it is bigger or it's the most weighed element in the list. So essentially, binary trees, but like we mentioned previously, they're using recursion to solve different types of problems. It has a height as well to indicate the number of levels that are in the tree. And like mentioned earlier, we're usually only working with half the data at the time to reduce the work. And every binary tree is going to have a root, which is the core of the tree. It indicates that is the first element when we try to access the tree. And then, of course, every node is going to be pointing to two leaves, a left node and a right node. These can be child nodes, these can be called leaf nodes, or these can just be called nodes, right? But essentially, there's going to be two references to two different nodes. And so here is our visual family tree that we're going to be doing for The Simpsons, right? We start at Lisa as the root, and her parents are both Marge and Homer Simpson. Mothers are going to be pointing to the left, fathers are going to be pointing to the right, and so Marge's mother is Jacqueline, Marge's father is Clancy. And same thing over here, right? The mother is Mona Lisa. I'm sorry, Mona Simpson, and then over here we have Abe Simpson over to the right for Homer Simpson's dad. All the way up this list, so on and so forth. And so we're going to use the concept of a binary tree to add these people to a family tree and be able to search different types of information that we're trying to find. So let's get right into it. That way we can actually see how we're going to be demonstrating and how to actually build and code a binary tree. To get things started, right, of course you need your tree object, right? In this case, we're calling it a family tree because we're using family members inside of it, right? So the first thing is the data set that we're working with, right? So the data that we're working with is a family member, okay? And then the nodes that are pointing it to, we are calling it bio mom and bio dad. You can think of this as the left node, you can think of this as the right node, but these are basically the references to the next node within the actual tree. I created two constructors here, one that takes a string first name and a string last name, creates a family member object with that, and then sets it as the root. The other constructor actually takes a family member and sets it as the root, so it makes one less step easier there. And then, of course, we have our setters and getters for each of these three field variables. So we have set root, set bio mom, set bio dad. Each of these taking a family tree object or family root, family member root. Now when it comes to our getters here, same thing. We have our get root, get bio mom, get bio dad. Okay, so now we're inside of our main method here, which is going to be creating a family tree for us, right? So in order to do that, we create this as like a normal object because we created the class for this. So we're indicating a family tree type. We're naming it root for our situation. And then we're going to be creating a new family tree. And we're setting Lisa Simpson as the first, excuse me, as the first person in the actual tree. So now what we're doing here is now we are calling the root and we are setting the biological dad to be Homer Simpson and we are setting the biological mom to be Marge Simpson. So to get a visual understanding, right? We've already created Lisa. We have set biological mom to be Marge and we've set biological dad to be Homer Simpson. And now, if we wanted to set Homer's parents, which are Abe and Mona Simpson, the way we do that is we start at the root, and we're going to get biological dad. So that means that we start at Lisa, and then when we get biological dad, we are getting Homer Simpson, right? And the next line of here says set bio dad. And then we're going to do the same thing for Homer's mom, right? So we're going to start at the root. We're going to start here. Then we're going to get biological dad right here. And then we're going to set biological mom to be Mona Simpson. So we're here. We set mom to be this. We pretty much follow this path here all the way up until we have every member on the list. And this is what it'll look like once we've added everyone to the list. So I'm not going to go over each and every single one of these, but let's just kind of stick with the ones towards the end so we can get a good idea of how this is actually searching and being done. So when we go right here, right, so we are setting Yuma Simpson's parents, right? Yuma's up here. And so essentially when we are starting, we're just going to make sure that we have this highlighted to make it easier to see. But we are going to start at the root, and then we're going to go to get biodad, which is here, and then we're going to get biodad again, which is here, and then we're going to get biomom, which is here, and then we are going to set biodad. So we're setting the dad to be John Hickman. Yeah, oh, I guess there's a misspelling here. My apologies. But then we're going to go in and we are going to do the same thing. We're going to start at the root, travel until we are able to set the mom, which is Leanne. And so that is how basically we are, we create a tree and you add nodes to the left and right side. Now let's actually see how we can search things and do things with this tree. Alrighty, so let's go in and let's talk about how we're going to be actually navigating and using and finding specific information from a binary tree. The first thing that we're going to be talking about using the tree that we created here earlier today with the Simpson family tree. First, we're going to go in and we're going to figure out how to print every single element and print its, we're going to print the root and we're going to print the parent name as well for both of the parents. So then we're gonna go and figure out how to find the very first Simpson in the family tree, how to traverse it and figure out which one is the very first one when there's no more Simpsons before them. And then we're gonna find the very first mom and the very first dad in our family list, which are gonna be at the very top here. So if we go into our print family tree method, let's bring back our family tree here. Here all we've done is we've just added some print statements. We haven't really done anything searching. We haven't really done anything recursive at all to go through these nodes. All we've done is added some print statements, right? So every node that we're going to go traverse into is going to do this here. So every node is going to print its name, and if there is a biological mom, it's going to print her name. If there's a biological dad, it's going to print the dad's name. Then it's going to print a new line. So if we just run this, all this is going to do is just going to print the roots information. That's it, because we're not actually traversing through to anything. We're just printing it. So if we wanted to actually make this recursive, then we need to add some type of line of code that is going to allow us to proceed to the next node and then actually and call the family tree method all over again. So that way it keeps doing so until it reaches the end. And what we can add here is very simple, right? So the very first statement as a recursive is an if statement. So if there is a biological mom, we want to call the mom node and call the print family tree name under her name essentially. Once her entire family tree is printed, then we're going to go proceed with dad's family tree and print that. And then once we printed that, then it executes, and then this is all done. So now that we've added these recursive lines of code, let's run this here. And there we go. We have our whole entire tree printed here. Every node with all of its information printed. So we started with Lisa. We printed her Marge and Homer Simpson, which is right here. And then we went in and we traversed through to the biological mom, which was Marge Simpson. We printed her parent information. Then we proceeded to her mom, which was Jacqueline Bouvier. But if we notice, she doesn't have any information, so it ends. Then we proceed to Marge's dad, which is Clancy Bouvier. Then there's nothing else after that, so it terminates. Then Marge is all done. We go back to Lisa, and then now we call Lisa's dad's side's information, right? And so this is when it starts picking up with Homer Simpson instead, so on and so forth until the very, very end, until we have all the nodes printed out here. This gives us a good information for the tree. Now let's proceed with getting the first Simpson in the family tree, right? So how would we actually do that, right? We always want to start with the parents, right? We want to make sure that the parents even have the Simpson last name. And if they do, we typically want to lean in with dad's side, right? Because mom probably had a last name change to match dad's, right? Not every case, of course, but in this case, yes, here. So we're instead of going through mom's side to find the very first Simpson, we're going to go through consistently going through dad's side to find the very first Simpson. So we go through with Homer, we check to see if there's any Simpsons. There are, so we want to go in with dad, right? So now we're with Abe Simpson. Both of his parents have the Simpson last name, so let's go back up with his dad. Right now we're with Orville Simpson. For whatever reason, right, during their move over, whatever happened, Orville got a different last name than his parents, right? So he is technically the very first Simpson in this family tree. So how do we actually implement this in code? Fairly simple, right? Just two statements, an if and an else, right? So first thing we want to check for is we want to check if there's even a dad to go up to, right? So if we don't have any information to go up to, then we're just going to return the root, right? Because there's nothing to find. We're just going to return the root. Or in the case where if the biological dad, if the last name does not equal to Simpson, right, then we know, hey, the next parent up are no longer Simpsons, so we want to return the root because we have found the very last Simpson in the tree because there's no more Simpsons after these parents up here, right? So if the biological dad, if his last name is not right here with the exclamation point not equal to Simpson, then we return the root. So when we run this, we output that the first Simpson is Orville Simpson. So essentially, we go, these are both Simpsons, so we go to dad, right? His parents are both Simpsons, so we go to his dad. Again, all over until we find Orville Simpson, and that's what we find here. So pretty straightforward here. Now the next thing that we're going to talk about is how to find the first mom and the first dad. Okay, so from what we know from family trees, right? We know that the very first person to be in a family tree is going to be at the way top, right? So we know that just by looking at it, the first person is up here. But the code doesn't know that. The code only can go from here to all one by one. So how are we going to actually guide it to get to here without knowing that this is where it needs to go? So remember, all trees do have a method, or you can create a method that calculates the height of your tree, right? So essentially, we can use that to our advantage to say, hey, what is the height of this side? What is the height of this side? And if this side is greater, okay, well, we want to go this side. And then same thing, well, with Homer, which side is greater? Mom's side or dad's side? We were in the height. Obviously, we're going to get a height much greater over here. And then it's going to decide to go this side. And then at that point, these are going to be the first parents on here. It's just going to pick the left side first just to make things easier. But when it comes to the recursive case, right, if we want to find the very first dad, first thing we need to do is we need to see if we're at the root or not. If we're already at a root, we're just going to return the root, right? That means that either we were at the root to begin with, or we have already found the dad, the furthest dad that we could go and find. Now, if we want to make this recursive, right, the other situation is if the parents are null. The other outcome is if they are not null, meaning that there are nodes. And if there are nodes, what we want to do is we want to find the height of the mom's tree, right? And then we want to find the height of dad's tree. Using this method here, it's going to count how many levels, right? So Lisa Simpson would be 1 level. This would be 2 levels. These parents right here would be the 3rd level. This would be the 4th level, and then the 5th level. So we'd be finding the level of each side over here. So Marge's family tree would be 2 levels, and so on and so forth, right? And depending on which, if dad's tree height was longer, then we're gonna proceed and call dad's side, and we're gonna start trying to find the first dad through his side. Otherwise, then of course that means that mom's side was longer, and we're gonna want to find the first dad through mom's side instead, all the way until we traverse the very top. So that is all. We have reached the end of the Java Collections tutorial video. We've covered a lot of different Java collections and structures to store information, but now you have a good grasp of different ways and techniques to store information, just depending on the type of information that you're working with. So I hope this was helpful for you. So you can start storing your own information and even building your own code as well, building your own structures as well as needed, or customizing them as you need be. So thank you so much for watching. This is Julian Sanchez, and enjoy the rest of your day.